In this tutorial, we are going to model the stability of slope which is given in the figure. We have been given embankment, or you can say a dam, which has got the slope, and then this slope is uh, divided into two layers. There is a top layer which has got certain unit weight, cohesion and angle of internal friction. The bottom layer also has certain unit weight, cohesion and angle of friction. There is a water which is inside the dam or embankment, and then on the other side there is a downstream of water level. Technically, you could also do this by using CW first, followed by slope stability analysis, or you could just directly do this slope analysis provided you have the water level. But this water level needs to be established in order to process it from CW. In this example, we will do a slope W tutorial. We have been given a geometry with a water level inside the dam, and then there is a water level outside. So we will continue to model this slope and find the factor of safety of this slope using multiple different methods. Initially, I'll show you how to use it by ordinary slices, and then we'll go and do the same thing for other methods as well. Open the Geo Studio software. Make sure you are using student license. The other thing is our geometry for this problem is in metric system, so use the metric. If it is in US customary unit, you can always use imperial units, that is US units. And then these are just the paper sizes. Okay. Then the next step is to open the slope W. Now, by default, it chooses Morgenstern price method. I am going to change that to method of ordinary slices. Now, here it is a slope W analysis. You can have your description entered here, whatever you want to enter. Let me say it is a tutorial. And then for water pressure conditions, you could technically use it from other analysis or parent analysis. But in this case, since we have been given the piezometric line or the water table, we will tell the software to use it from that line. There is you can say there is something known as phreatic correction for the internal water line. That's a different topic, so I'm not going to get into that detail, but you can choose that, or if you are using other CW analysis, then it would automatically calculate that. Then stage pseudostatic analysis, we are not using any staging. You could technically construct the embankment and then have the static analysis done first before running the slope analysis. So there is no stage pseudostatic analysis. There are no partial factors. Now, second thing is to check on the slip surface. Now our geometry, the first thing is whether it is the slope will fail from left to right or right to left. Now look at the geometry. The geometry says that the slope, if at all it fails, it will fail from left to right in this direction. So let us go back and choose left to right. Then we are going to use the entry and exit method. So we will have to specify where the entry points are, where the exit points are. You do not have to choose this radius and tangent lines, so leave that alone. We are not going to use grid and radius. We can always say optimize critical surface location. It might ask you optimization settings, so number of iteration 2000 or minimum difference in factor of safety, all those things you can leave it as it is. Then the next thing is factor of safety distribution. Keep it by default, whatever is chosen, it is constant. For advanced, you can choose slip surface depth. So minimum, if there is a depth of 0.1 meter, it will take it. If it is smaller than that, it will not call it as a slip surface. Number of slices you can control. You can have 30 slices, you can have 10 slices, it doesn't matter. I would suggest initially when you are starting, leave the option which is by default. The number of iterations here 1000, and tolerance of factor of safety is 0.001. So unless the factor of safety changes by 0.001, it will not affect the problem there. So close. You can always save this wherever you want to save. So I'm saving it on desktop. I'm calling it as slow tutorial. Now the first thing is to set the scale and geometry. So use units and scale. So this is in metric. So make sure this is in metric, this is in kilonewtons. Do not worry about reference scale, and of course this is a two-dimension analysis. So say apply and say OK. Then the next thing is to sketch the axis. I always prefer to do this because sketching really, it gives you some point of reference to draw. So on y-axis it's my elevation, and that is going to be in meters. And give the units. This is going to be distance meters. Now font size, you can have it whatever you like. Then x-axis starts at 0. Maximum x-axis we require is 40, but let us say we can have about 50 meters. As far as y-axis is considered, it starts at 0. We require about 14 meters. Let us say we go up to 20 meters. So the first thing now is to draw the geometry. So select sketch. So either you can sketch from here, or you can go to sketch and then choose polylines or simple lines, whichever you want. Okay. So let us say I am choosing polylines, and I will need to draw the polyline. So I will start from 0, 0 here. I have first 14 meters. The next would be to draw the regions. So go to now draw regions. And just draw the regions for two different soils. So first region is the bottom part. This is the first soil layer. The second soil layer is on top. So now we have drawn the regions. Now you can create materials. You can always go into key in materials create materials and then apply those material properties. So I'm going to add a new material. I'm going to call it as then I'm going to choose Coulomb as my model. The unit weight would be, it is given, it is 18 kilonewton per meter cube. Cohesion for the bottom soil has been given as 10. Envelope internal friction has been given as 25. You can choose the color if you want it. I'm going to just add, or you can always clone it and then change the name. So instead of my bottom, then there would be top layer. And then properties are 15 kilonewton per meter cube. And then cohesion is 5. And then P is 2. So we have created 2 layers of sides. Now we are going to apply those layers to the given. So the bottom layer, choose the bottom layer and then bring the cursor in the bottom layer and click it. Same thing we can do it for the top layer. Choose the top layer, apply it to the top layer. The next thing is to draw the isometric line. So you can say number 1, draw the water line. Click that. So we have our model that is set up, and we are all ready to draw the next step, that is to draw the surface entry and exit point for the slip surface. Now remember, if this slope has to fail, it will fail from left to right. So our entry points will be on the top and exit point for the slope will be on the downstream side. So click on draw the surfaces and then range. We will choose that range. So click on left point and drag the mouse button from here to here. Then click on exit range, which is between these points. Now you can change number of points. Instead of right now it has got 4, you can change those points to number of points. So instead of number of increments over range, you can have say 10. So it will have more circles to check. So save it and we are all ready to run the analysis. So click on Soil Manager and that should be start. So now it has run the analysis and it shows you the minimum factor of safety for a particular circle. It ran through hundreds of slip surfaces and it found out a particular critical surface which gives you minimum factor of safety, and that minimum factor of safety happens to be 1.204.